we can all join this same plan together. So today we're supposed to cover ground lesson 1, ground lesson 2, ground lesson 3, which is not too terribly bad, except that nobody had a book. Tomorrow everybody has books, right?
You're talking about Jepson book?
Yep, that one right there. That's the one. Now, a lot of this will work a whole lot better if we do, the reading assignments, because so some of this is designed kind of a, some of it's a lecture, some of it's a little bit of a let's ask the question and see what you got during the reading. So it works a lot better if we do the reading ahead, and especially we get over there and they don't have any background at all, the reading is going to be key to their success. So do the reading ahead of schedule, and then we do have, so tomorrow, for instance, is supposed to be a stage 1 exam. That's important if we're there with them just a little while, because we got to see who's getting what. Here, we got a little bit of time to do the stage 1 exam, so maybe not, in the classroom, but we figure that out.
You have papers?
We have the papers.
For exam?
Yep.
Good.
And they're right there in the book. So, for instance, if the pilot wants to come in and say, you know what, I've got my exam completed, okay, that works. We're going on an integrity system, but I think it works out.
You're talking about questions from here, end of chapter?
End of section has them, and then also we have the stage 1 exams. Now the exams are available to purchase all on their own. They're a standalone product as well. But yeah, those exams really give the check on learning.
Well, you will have it on paper.
Yeah, we'll take them with us so that we have, hey, this is the exam, everybody open page 1, you got an hour to finish, and then we finish it up and we stay on schedule. But just so we're all, on the same page, so today ground lesson 1, 2, and 3. No problem, we'll finish those. We're cooking along here pretty good. Tomorrow morning we'll start off ground lesson 4, ground lesson 5. And you can see that's the study material for that is chapter 4, chapter 5. Then as you move into the afternoon, 7, 8, and 9, and then continuing through, you'll see this is a little bit of a modified class on an adjusted timeline. But here we go with section C, flight instruments. So let me reset this guy. And that's that. International Standard Atmosphere. So how did they come up with this idea of calling standard temperature? Scientists came together, I don't know how, they've been studying the atmosphere for years and years and years, and collectively they decided internationally, worldwide, that 22.92 inches of mercury is standard. That 15 degrees Celsius, which corresponds to 59 degrees Fahrenheit, that's standard. Okay, let's talk just for a second about 29.92 inches of mercury. We toss that term around like an old sack of potatoes, right? But we never really focus in and think about what does 29.92 mean. So here we have a container of liquid mercury, okay? And then inside that container, they push a vacuum tube, okay? Vacuum tube meaning what? Well, there's nothing in there. It does not contain any pressure at all, right? So effectively, there's zero pressure inside this vacuum tube. And submerge that into the mercury. So the only effect that you'll get on the scale is the effect of atmospheric pressure. And how far will that cause this mercury, this liquid mercury, to rise? Okay? Like I said, internationally, it was decided and agreed upon that 29.92, or roughly 30 inches of mercury at sea level, was your standard pressure. Okay? There's a lapse rate for both of these, and we'll talk about them. As far as temperature, 15 degrees Celsius, that seems a little cold to me, but that's standard temperature. So, airplanes use that exact same pressure and temperature and air density to measure some of the indications we see at the flight deck. So we have a pitot-static system. There is a pitot tube and static ports. The pitot tube is connected to the airspeed indicator. Now this pitot tube is interesting because it's sticking out off the airframe somewhere, whether it's a wing, the fuselage, whatever the case may be. It protrudes into the relative wind. So you get dynamic pressure introduced into the front of this device. Okay? Dynamic pressure comes through the line and enters a diaphragm, which is geared and causes the airspeed indicator to move. Now, certainly, could these be digital instruments? Sure. And then you have an air data computer, and it provides some sort of indication on a symbol generator or an electric screen, LED screen, whatever the case is. But the system still works essentially the same. It's just how are the displays. This is a very simple display, so we use, and plus, it's the display that you use in the training environment, so this is what we're using for the class. So dynamic pressure comes in, enters the manifold, right? And that manifold expands and contracts as that pressure enters or decreases, as it increases or decreases, which causes an indication here of airspeed. As we climb, though, what happens? Less pressure. Fewer air molecules, which cause less pressure, less dynamic pressure in this diaphragm. Okay? That would mean that as I climb, I get a lower and lower indicated airspeed. Well, I do, but there's something that also allows for some of this to not affect our indications as much, and that is the static port. Somewhere on the airframe, usually on the side of the fuselage, near the front, near the back, whatever airplane I'm flying, we get a measurement of static pressure. So no pressure entering the tube, like here I have pressure entering, air entering the tube. On this, it's just a measurement of static air. What's the pressure here? The static pressure. That pressure is on the opposite side of this diaphragm. So the diaphragm is filled by dynamic pressure, like this. But on the opposite side, on the opposite end of that diaphragm, is static pressure. Think about a balloon. If I released the helium balloon, it would float. Okay, forget the helium because that part's not important. But as it floats and as it goes up, what happens to this balloon? This balloon will expand. Right? Did anybody see Baumgartner jump off the balloon from space? Did you guys see that? He parachuted from outer space? No? Oh, great. Well, anyways, he had this balloon that looked like just a long bag, right? And when they released this thing, all it was just it barely looked like it was going to float at all. And as he went into space, this thing expanded and became humongous, right? So before he jumped off that platform, he had an actual balloon. As it goes up, as you increase altitude, the air density decreases, and then the pressure on the inside, even if it stays the same, it continues to increase the volume of that diaphragm, what we have here. So we got a diaphragm. The diaphragm is expanded by dynamic pressure, but on the outside of that diaphragm, there's less and less pressure as we climb. So I get a more accurate indicated airspeed. We will talk again in one of these subsections about the different types of airspeeds, right? Indicated, calibrated, true, Mach index number, all this good stuff. So just keep in mind, kind of park that in your brain for a second, that this does come up again later, but essentially that's how this device works. The pitot tube. The pitot tube has a drain hole somewhere on it. In this example, the drain hole is here. I can tell you it's important to check airplanes if you're going to rent them, if you're going to fly them, whatever. Check to make sure that the drain hole is clear. I've seen airplanes on this ramp, not in this school. We really do a pretty good job here from the very beginning of maintaining the airplanes. But I've seen airplanes on this airport that had recently been painted, and the Pitot Tube was painted as well. And the drain hole had nothing but paint over it, okay? So there wasn't a chance in the world for that drain hole to operate or function properly. The idea behind this drain hole is this allows contaminants to escape. What type of contaminants? Well, the number one is water. Water vapor, whatever, some sort of condensation, moisture. When moisture gets inside here, it could adversely affect my readings. So this will allow that moisture to escape. Okay, we'll talk about failures here in a moment. I think I got some nice slides that'll do better than me just sitting up here talking about what happens when these things fail. Just know that I have a ram air inlet and a drain hole that will allow some debris or some contaminants, primarily moisture, to come out. Static ports. The static ports connected to the airspeed indicator, we talked about that, but also connected to vertical speed and altimeter. Altimeter is a real simple device. We already talked about it. As I increase my altitude, the pressure surrounding whatever kind of balloon or diaphragm or aneroid wafers that I have, it's a real word, aneroid wafers. So it'll allow these diaphragms to continue to expand and then give me a readout here for my indicated altitude. So as we go up, the diaphragms expand, it's geared to that dial, lets me know. This has a Colesman window on it, which will allow me to adjust for non-standard pressures. Now that Colesman window is not required for VFR flight. This is a VFR class. Private pilot, VFR. So I don't need this thing at all. There are very few of them, but there are some that are just altimeters. What I need this for is IFR flight, okay? So just know that. And a lot of times that's what will give me a NOTAM if the pressure reading is over, I think, 31 inches or less than 28 or whatever, because some of these didn't go beyond, just a NOTAM is published, okay? Vertical speed indicator. This one is a little bit interesting, a little bit fun, because there is, again, a diaphragm, but it has a calibrated leak. Okay? So this doesn't always give me an instantaneous indication of the conditions surrounding my airplane. Okay? That's going to give me a more instant or instantaneous indication. If I see my altimeter moving clockwise, guess what? Clockwise this way. If I see my altimeter moving clockwise, I'm climbing. If the altimeter is moving counterclockwise, I'm descending. It's not uncommon, if I'm doing maneuvers, that my altimeter may be moving clockwise and the vertical speed indicator indicates still a little bit of a descent. And you'll look for that split second if you notice it. Right? You'll look and you're like, what the heck is going on here? Okay, that's okay. This has a calibrated leak, meaning that there is pressure contained within a diaphragm, but it leaks out at a certain amount. And this will eventually catch up to, in a stabilized condition, this will catch up to and display my vertical speed, whether it's up or down or whatever, okay? All right, let's go through some slides. So, a couple of things that I got on an airspeed indicator. Different airspeeds. This is a common single engine airspeed indicator. It also has a flight computer. I love the flight computer. God bless it. If mechanics would just help me out with this thing sometimes. So what do these arcs mean? Let's go through them. Anything white is going to give me some sort of flap operating range. It doesn't mean that this is the flap operating range for all flap conditions. This is my full flap operating range. So consider the placards, consider the AFM. I may be able to extend an intermediate flap setting, like an approach flap setting, at a higher airspeed. Okay? But before I'm at full flaps, I need to be within this white arc. So I have a stall speed at the lower limit. Stay with me. I'll explain lower limit in a moment. I have a stall speed at the lower limit for flaps. I have a stall speed at the lower limit for the normal operating range. In other words, clean configuration, or what they'll call a specified configuration. Okay? So these are the stalling speeds. We'll talk aerodynamics in a moment, so I'm excited to talk stalls with you guys, believe me. Wide arc, we said already, that was flaps. VFE, velocity flaps extended. The green arc, consider this your normal operating range, okay? But that also gives me something called V no. Not V yes, but V no. V no, and then all of a sudden pilots are in a tailspin. I don't have a clue what V no means. It's okay. It's just normal operating. This is the upper limit of the normal operating range, okay? The yellow arc, it's your caution range. Now, caution meaning you're not fighting some sort of turbulent condition. It's not uncommon for me to operate airplanes in the caution range. Okay, this is okay. Fly it by the AFM. If I have the airplane in smooth air, this is great. This is a perfect place for me to be. But not above the radial red line. And they'll call it radial red line. It's right here. The velocity never exceed. You don't exceed that one. There are a couple of other airspeeds that could be on here. But one of the other airspeeds that is on here is a true airspeed. True airspeed in knots. I encourage you, before flying on your cross-country flights, to become familiar with your flight computer. It's right there. And it's adjustable usually with a knob either here or here, wherever that knob may be. On some airplanes, it's adjustable by moving it manually. So I think on the Cessna 172 November, you just grab this part of the flight computer, the inner wheel, and you just move it where you'd like that to be. Okay. How many times have I flown with pilots that are, man, I am ready to go for my check ride. I can't wait. I'm so ready that Nielsen's going to write a book about me. I'm going to write a book about you, all right. I've got a book similar to that. It's called Does This Mean I Fail? It's written by Brooks Black. Okay? How many pilots I've been with, and we do a stage check, and very first thing I do is we're going on a cross country. So that's where you're taking me. We do a little mock oral, right? I do the stage check and go through the oral exam part. Today we're going to fly to Tampa. So when we leave today from Fort Lauderdale Executive, I want you to prepare and leave just as if we're going to Tampa. 9 times out of 10, the pilot says, we're not going to Tampa, are we? Of course we're not going to Tampa. Okay, it's a stage check. It's not a cross country. But we're going to leave here with a scenario like we're going to Tampa. Okay, so that means that when you take off and you didn't set any kind of timer at all, you have no idea when we took off. 10 minutes from now when I ask you, hey, when do we get to your first checkpoint? How long have we been flying? And you have no idea. Maybe not a great execution for a cross-country flight, right? Just, you know, interesting tidbits. The other thing, we get to your cruise checks. Hopefully you did your climb check. A lot of times they don't. We get to the cruise. Now it's time for your cruise checks. Hey, did you do a cruise check? I've never done one of those before in my life. Is there such a thing? Yeah, well, there's a cruise check. Let's get that going. And once you get the cruise check complete and we're actually headed towards Tampa, and you start looking outside, now you're into your flow, what's our true airspeed? And the pilot undoubtedly will tell you, yeah, my true airspeed is 105. Well, what did you plan your cross country for? 121, but these airplanes suck. They're old. They'll never get 121. I don't know, you know, just old airplane. Okay. What do you think our true airspeed is? No clue. Not a clue. Well, how do we figure that out? Next thing you know, they got an iPad and a calculator, a pencil, 3 pieces of paper, and they're still no closer to finding true airspeed than I am of flying that Cessna to the moon. Okay, that's about how close they are to getting this thing. Nowhere even close. There's a flight computer right here. Move this until your pressure altitude, let's call that whatever your altimeter says. Because look, 1,000, 2,000, 3,000, I don't think that little 0.1 inches of mercury that you'll adjust from standard altitude or from standard pressure is going to make a big difference on that scale. So if we're flying at 4,500 feet, take 4,500, move this until it's underneath of your outside air temperature. Every one of these airplanes has an outside air temperature gauge, okay? Move this until you get to your outside air temperature, and then the needle will point on the outside scale to your true airspeed. Who knows how to use that? Nobody. Because it shows you, oh, of course you do. Because it shows you on the digital displays, doesn't it? What's our true airspeed? Mach 0.87. Oh, great, there you go, I got it. Okay. It doesn't show you that in here. We got to figure out the basics first. Why are you at Mach 0.87? You don't know what true airspeed is. This is my question. All right? So that's true airspeed.
Actually, I think it's a good idea to point out on this slide, I mean after this slide, what kind of speed we have on the airplane. Because probably for gentlemen in the back desk, they understand we have 4 different airspeeds. But for Vladimir, I believe, and maybe for Alona, it's going to be kind of surprise how many speeds we have.
Sure, yeah.
So better to explain what does it mean.
Well, again, the whole idea is this is supposed to happen the day after they read the material.
Right.
So the only way that this course happens in 35 hours is if you guys have showed up and you've already read the material. If you haven't read the material, then the 35-hour course becomes like a 200-hour course.
Yeah.
All right. Now then, we've got altimeter. Static port, again, where does it go? It charges the case. In other words, the static port is piped directly into the case. And then here are your aneroid wafers. I told you guys that was a real word. I thought I was making it up.
Almost the same.
What's that?
Aneroid membrane.
Say it again.
Aneroid membrane box.
Okay.
Yeah, in Russian.
Oh, okay, I got you.
Correct, yeah, but
Same thing, yeah. So aneroid, it sounds like a funny word though. Whichever language you use, still aneroid. You're like, what the world's going on? So aneroid wafer is connected here. Just like I promised, there's gears that are attached, and then that will allow me to see or read my indicated altitude. Okay, comes from the static port only. You got the 100-foot, 10,000-foot, 1,000-foot marker. A crosshatch flag will show when your altitude is below 10,000 feet. So I don't think any of our altimeters on these airplanes have a crosshatch flag. That little section on the bottom, that'll show if you're below 10,000 feet. Okay, just a couple of key points. If you're taking a look at this thing, make sure you're reading the 10,000-foot marker first. Because this one, it looks like 8,000 feet. Okay, great. It's less than 10,000, so yes, it is 8,000 feet. This one, that's not 2,000 feet, is 12,000. So just quick, how do we do this thing?
And this part is a question from written tests, as I remember. Right?
These are, yeah. All right.
Oh, yeah.
True altitude, absolute altitude. There's a couple of different types of altitude. Okay, notice how, and this will really reinforce the weather section. Notice how we got what's called a 1,000-foot pressure level or a 2,000-foot pressure level. That means that airplanes that are flying along that level are using a certain altimeter setting. Okay, whatever pressure level that is. That's the pressure that we're using for this area, and that airplane shows 5,000 foot in every one of these altimeters. Okay? But this is definitely my true altitude. It does matter what the temperature is. Because if we go back just one slide, take a look. This whole thing runs off air pressure and air density. All right? So if I have different air density, i.e. different air temperature, my airplane will be at a lower altitude for a lower temperature than it is at a higher temperature. So This feeds a lot into the instrument program where I may not be able to descend and use a certain approach if the temperatures are lower. Because it implies and it shows exactly, this proves that I have an airplane with an altimeter that indicates 5,000 feet, but I may be much lower than the other airplane showing 5,000 feet in a different area with higher temperatures. So as I'm flying into a low temperature area, the absolute altitude, the actual altitude of the airplane is closer to the ground. The entire static system works off of air density, so much lower to the ground here. Okay, couple of altitudes that we have. The standard datum plane. Give me a moment, we'll get there. Let's work through some of these other ones. Sea level, that's just where sea level is, okay? That doesn't mean necessarily that it has anything to do with standard pressure, okay? It's just where the sea level is for these conditions today and in that geographical location. Above sea level, you have terrain features. The terrain features will show, hey, maybe I have a big piece of rock that extends up to 5,000 feet. Okay, we've got something like that in Colorado and Nevada and all that. There could be mountains or any other type of terrain. In order to interpret how high I am, we need to come up with some sort of terminology. The absolute altitude, or AGL, right? The absolute altitude is how high my airplane is above that terrain feature. Now we could be on a terrain feature that's large enough that you just don't see how high it is protruding above sea level. You may be on top of rock shelves that are in Tennessee or whatever, you're 700, 800, 900 feet above sea level, but it looks like it's all flat. You're still above some terrain feature, and that's your absolute altitude. Your true altitude is your height above mean sea level. So here I go, I got mean sea level. What's my height above mean sea level? This is an airplane flying set to the proper altimeter setting. Wherever I'm flying at, I know that my altimeter setting, whether I got that from ATC, Flight Service Station, whatever source I received this from, I know that my altimeter setting for the day or for that area is 3010. Great, I got it set. My altimeter shows 5,000 feet. That is my true altitude. That doesn't mean that I could be 5,000 feet above the terrain. I may only be 3,000 feet above the terrain. So 3,000 AGL at 5,000 above the sea level. Everybody okay? If I'm moving fast with some of this stuff, let me know. Because is everybody good? Okay. The pressure altitude. This is your height above the standard datum plane. Now, pilots, people, anybody, I don't care what nationality you are, what your first language is, what your first 12 languages are, it doesn't matter. This gets confusing because we're talking about something that I can't hold. I cannot touch the standard datum plane. It exists as an idea. And once we get to one of these places where it exists as an idea, people get a little bit, I don't like it, okay? So here it is. Can I reach out and touch this terrain feature? Yes. Can I reach out and touch the sea? Yes. This I just told you, we cannot reach out and touch it. It depends, and it's calculated. Remember, this is not a real thing. It is a plane, okay? I got a point. 2 points make a line, straight line. And if I got 3 points that are not in a line, if I got 3 points, it makes a plane. So we can call the top of that table a plane segment. And if it went on forever in all directions, that would be called a plane. Okay, not an airplane. Maybe it gets confusing because it says plane. It's not an airplane. The standard datum plane is calculated by what is the current pressure where I am compared to standard pressure. So if my pressure is not standard, this standard datum plane is either above or below sea level. And my height above that standard datum plane is my pressure altitude. Now there are conversion tables. I could look at almost any aviation publication. It will show me my conversion tables. Anybody ever seen one? No, of course not. Who cares? I'm not looking at that. Why? Because I get 1,000 feet difference in 1 inch of mercury. So if I go from 30 inches of mercury and now all of a sudden it changes to 29, that's a big change. That's 1,000 feet difference. Okay, and it changes linearly. So if I have a 0.1 change, it's only 100 feet. If I have a 0.01 change, it's only 10 feet. So going from 29.92 to 30.0, that's only 80 feet. In the grand scheme of things, it's almost negligible. But it exists, and it's important because at a certain altitude, once I get into the flight levels, once I get into class alpha airspace, once I get above 18,000 feet MSL, now I'm flying my airplane reference the standard datum plane. Okay? So it becomes